There's one problem that we still have with white LEDs, even if they have more than one phosphor. This whole process, putting phosphors on LEDs, is not a digital process. I cannot tell that let's lose 5 bits of phosphor and now we have a warm white LED. It's chemistry, physics. So you will never get 2 LEDs which are absolutely the same. Have a little bit more, a little bit less phosphor. Even the phosphors, they differ a little bit. I mean, it's chemistry. So the problem is that manufacturers like, let's say, Osram or Philips, they produce LEDs every day, millions of LEDs, millions, but they can say, okay, today we do warm white LEDs, yeah, and they will get warm white LEDs, millions of them, but they will not all look the same. There are LEDs which are a little bit more bluish or a little bit more greenish, whatever. And so they measure all the LEDs and they bin it. It's called binning, LED binning. Every manufacturer of LEDs does LED binning. And so now we have a bucket full of LEDs. They are all warm white, but they differ a little bit. And so you might say, well, doesn't matter if it's like a little blue, maybe I wouldn't, would I even see it? And I can tell you, yes, you will see it. This is from a data sheet from LED manufacturer, and looks a little bit weird, but I will try to explain. What we see here is these are the bins labeled by these letters here, QM, whatever. That's one bin, that's another bin, and here, this thin line, this is the black body curve, and this white point, this would be what we call tungsten color temperature. So here we have tungsten, and there seems to be a bin, whoa, yeah, PO called, which looks like tungsten. So if we want to produce LED fixtures for, let's say, TV studios, we are interested in this bin. We want to have this bin because this looks like tungsten. So we ask Osram or Philips, yeah, I want to have, like, let's say, 100,000 LEDs of PO. So Osram says, no, because everybody wants this, yeah. But the manufacturers, they of course want to sell all their LEDs. So it's usually not possible to get a single bin, or it's so expensive that you can't do it, yeah. Usually all manufacturers, if we are Ari or whatever, we have to buy more than one bin. And the difference between these bins, how big is the difference? Just to compare or to get a feel for it, I have these little colored dots here. So this colored dot, it is like tungsten with an 8 CTO, this color JS. 8 CTO, this would be quarter CTO, and the same 8 minus green. So the difference from this bin to this bin is 1/8 CTO. And if you're not still not convinced, then just use a fixture and put 8 CTO. Everybody sees this difference. Yeah, it's clearly visible. So the difference between bins are visible. And this is a problem that all LED manufacturers have, all manufacturers for fixtures. The problem that when you build or manufacture the LED fixture, called Bicolor. You might have already seen some fixtures that use Bicolor. Bicolor fixtures, they have warm white and daylight white LEDs, and you can just fade in between these two. So you can move on this line. You can have also 4000 Kelvin, whatever, but there's no chance to adjust something to the green or to magenta, whatever. You can only move here. It's only two-dimensional. So what Ari is doing, we have in all our fixtures at least 3 different colors. For example, the caster, these little panels here, they have warm white, green, and the blue LED, and we can achieve any color that's in between here. So if you get the feeling, looks a little bit too green for me, you can just dial out the green. You can adjust to any color in this triangle here. And the bigger units, the L series, they have an additional red LED, so this color space is even bigger. And with this, we don't have to worry about any differences of white LEDs or binning or whatever. It's not important for us because we always have the chance to just adjust the color. We can mix these LEDs that we have inside here very precisely, so we can mix them that all of these units are inside this white point. That's not a problem. Yeah. So there's no differences. You can like buy 100 of these units, line them up, they will all look the same. This is done by LED mixing. The nice thing about this, if you have a color space like this, you can also, of course, not only do color adjustments to get a nice white light, you can also do effect lighting. Here. Here we are. So all colors that are inside this triangle can be produced by the unit. And I made all these white dots. These are like jails, Roscoe jails. So as you can see, the unit can like simulate most of the jails. There are some outside, but 90% of the jails can be simulated by the unit. The nice thing about the color with LED is that if a LED unit produces color, only the LEDs that are necessary are used. So there's no loss of efficiency in this. If this unit, like now, produces red light, only the red light LEDs are illuminated, and so it takes around maybe 50 watts, not more, 50 watts to produce these red light. And if you compare this to a tungsten unit, with a tungsten unit, you have to always use jails, and every jail cuts away parts of the spectrum. This is how all the jails work. Want to get red light out of a tungsten unit, cut away all of the blue and green, and just leave a little bit of this, so you have a red light. So all these here, all this pastel part is lost. This extreme example is it if you want to achieve blue color with a tungsten unit. So as you see, most of these spectrum is now just cut away. And if we compare this now, if we compare efficiency of blue, for example, R7, which produces blue light, like here, to tungsten, jail tungsten, it's maybe 30 times more efficient. Now, color quality of these units. We had a look already, tungsten perfect. This is very, very bad color quality. The white LEDs are much better than this, but it's still not what we really want for high quality lighting. So this is the result what we, for example, get from these units. This is a spectrum which, like you can see, it's like a mixture of this and this. If you would combine these, you would get approximately this, and if you choose the right LEDs, you will get a pretty good color quality. So this is what we try, is to get a spectrum that looks a little bit like what we know from tungsten. And if we have a look at the results, it's also a test I made some years ago, a color chart. And what we see here is, as a reference source, a tungsten. So always the upper parts are the tungsten source, and the lower part is a warm white LED unit, so single white LED unit. And as you see with this unit, this had extreme color problems. It looked rose. This is mostly they look greenish. If you have white LEDs and compare them to tungsten, they mostly have a green spike, greenish. But it's also possible the other way around. So this was more a rose panel, completely different to the tungsten's rose. It was called warm white, but yeah, warm white can be everything. So what did I do to get a better result? The first thing I gelled. I tried to use gels, slight green gels to get the same white that I had from the tungsten's rose, and I did a quite good job. So now I made the white look approximately the same. Of course, I lost a lot of light with this because every time I put a gel on the unit, I lose light. But now I had at least the same color temperature. But as you see here, the problem is I can gel the light, I can do what I want, but I can't improve the spectrum. I can only adjust the color temperature. I cannot achieve a better spectrum or a better color quality in using gels. That's not possible. The color quality will stay the same, and so you will still see differences in the colors. And you could, of course, gel the light. Then, for example, this red will look the same, but then we will have differences here again. It's not possible to adjust a light or to get the same light quality by gelling a unit. Not possible. For example, here, this was now what we could achieve with the L7. Here, to get the same color temperature is pretty easy because it's like a continuous control. But also, if you have a look at the colors itself, it's pretty close to the tungsten. It's not perfect. It's not possible to get with LED an absolutely 100% perfect light source. You will still, if you look very close, see some differences. But for 99% of our customers, that's okay. They can live with that. So this is how Ari is doing it to get a good color quality with LEDs. And just to build a bridge to my last part of the presentation, high-speed photography, high-speed shooting. How do we do that? How do we control the LEDs to get this precise color? We use PWM. It's pulse width modulation, and this is standard. Nearly all manufacturers use PWM to control the LEDs. It's the only way to do it precisely. And how is it done? It's very simple. Switch on, switch off, switch on, switch off, and the LED just does the same. Light, no light, light, no light. And if we just shorten the period of current on, then we can dim the LED. And of course, this is done very quickly. So otherwise, you would recognize the flickering. But still, we have the problem if our eye might not recognize the flicker, the camera might. So if you have cheap LED fixtures that are maybe not even made for camera productions, that are made for event purposes or for architectural installations, they might flicker on a camera. So what we have to do if we want to use PWM, we have to do this very quickly. So these units, they work with around 20 kilohertz. So the flickering is so fast that even if you have a high frame rate in your camera, you won't see it. No problem. Yeah, you can shoot up 500, 1,000 frames. It's not a problem. You won't see the flicker of the LED. This is how LED dimming is done. Now, which is, if you want to do real high-speed recording, often you have to have a lot of light. So LEDs are often not strong enough, so you have to use HMI. HMI is the first choice for most people who will use high-speed photography, high-speed shooting. And if we look how the light is created with an HMI fixture, we have two types of ballast. These old conventional type of ballasts, they produce a sine wave. A sine wave, and if we have a close look, it like starts here, then we have a maximum, then slow. This is like a zero line to the other maximum, like this. And this results in a strong flicker. You always have minimum light, maximum if we are here, and then again minimum. So this is flickering. With these ballasts, if you ever worked with them, you know they flicker, and the only way to work with them is to adjust the camera speed to this speed of the ballast. So if the ballast works with 50 Hertz, the camera should also work with 50 Hertz, which means 50 frames per second, or 25 or 100. If you have a multiple of this, it's also possible. But honestly, these ballasts are only used in theaters nowadays because they are so silent. If we are on a location shooting, we have electronic ballasts. Electronic ballast is not working with a sine wave, it has a rectangular wave. And this is avoids flickering because now this jumping or this wave from one maximum to the other is very quickly. So this is only a small dash in the light. It's not, I mean, we call them flicker-free, yeah, but honestly, there is still a little bit of flickering is still inside these units. But if you compare to LED, which is like this, of course, it's much better here. So this is why with an LED, we have to work with kilohertz, like I said, 20,000 hertz in this unit. And with the HMI, we can use much smaller frequencies. All of our flicker-free ballasts, they have 75 hertz, which doesn't sound much. Yeah, 75 hertz, that's not much. But because it's only such a small dash that we have in the light, it works. So you can shoot with these ballasts and don't need to worry that you have any flicker. But there's one except. This works fine if we stay in frame rates, let's say up to 150 frames per second, it's safe. It's safe, you can use a standard ballast, you won't see any flicker. You can even go above this, but it's not guaranteed. It's not guaranteed, there might be some flicker. If you want to do real high-speed shooting and let's say use 500 or 1000 frames or even more, then ARRI offers these kind of high-speed ballasts. High-speed ballasts, they have these red knobs, and it's completely the same technology that we have with the normal ballasts, but they work much faster with 1000 hertz. And with these ballasts, you can shoot up to 1500 frames without any problems. You can even go above that. I mean, we made tests by ourselves and used much higher frame rates than this. It's all flickering is not. It's not that I have like 1501 frames per second and then I see flicker. It's not as easy as this. And there are many ways to avoid flicker. I just have made this small list. What you can do if you experience some flicker or you're not sure if there's something. One thing you could do is soften your light source. If you have a bigger light source, then it's always better. And there's always a better chance to avoid any flicker. So use a big light source, and yeah, it's quite natural. Use more than one light source. Just different fixtures, just not use a 9K, for example, and as your only light source, use maybe 3 4Ks or something like this, so you will have less problem with flicker. And of course, you can always try to adjust the camera. It's not only that you've been from very former times when we had the old conventional ballasts and we had to adjust our camera speed so we don't see any flicker. This is still the same method and still possible even now if we work with a high-speed ballast. Yeah? You can try to adjust a little bit in the camera to avoid flicker, and of course, yeah, use high-speed ballasts if you have them. All right, that's so far from my side. Feel free to ask any questions, now or later. Yes?
So this new color rendering meter, so I mean with the old one you can see, okay, I've got a bit of plus or minus green, so I'm adding magenta or whatever. What's the reading out of that? How can you...
It's there. Where is it, by the way? Here it is. Don't steal it. There are different modes in these tool. So because this is not an array tool, and I'm not honestly I'm not responsible for this. Yeah. So I don't want to make like too many.
Yeah, but you would use it to test your lamps, for example.
Yes, because this unit, it saves me, for example, it saves me an exact CCT value, color temperature.
Right.
And it tells me something about the CRI, about the color quality.
Right.
It uses only CRI, so as you learn CRI, I don't know. But at least it says something. And you can also have a look at the color space, the color spaces I showed you. So if I measure a unit here, it's quite small now. I hope you can see anything. You see where this fixture you measured, where it lies inside this color space. So if you see it's just below the Planckian locus, you know I need a little bit of plus green. Yeah. But you are true, it would be better if I see it directly, okay, like we know from our old color temperature meters, see like, okay, let's use this filter and then we will have it, yeah. In the end, it's only software. They could easily realize, maybe with a newer model of this is, they already have it, yeah.
The new one is also camera in the front, so you can directly get the part you're interested in, you know.
Ah, okay. And
so just now understand.
they are here, so yeah.
The new one.
I should be thankful.
What they call again?
Light equip.
Light equip.
Yeah.
It's just beside the array booth.
Very
Yeah.
close to the array.
Yeah. Yeah. They sell it. Yeah.
They have also to see the other value you call it.
Yes.
Yes. Not
Yes.
only the CRI, also the other one.
Ah, the TSI.
Yeah.
They are quick.
Yeah.
Yeah. I should have a look by myself, but I'm always here. I have no chance to go. Any more questions?